All right, greetings again, everyone. The purpose of this video is to go over another example related to partial fractions in section 3.4 in our textbook. Now, in this case, even though it says in the instructions here to use the method of partial fractions, we're actually going to approach this one from a different angle, if you will. So first things first, we want to try to figure out what's a little bit different about this problem, and in particular, I'm looking at the function on the inside there, as opposed to, say, this one that we have already done. Well, when I look at this one, what I notice is that the degree of the function on the top, or the highest power of the variable, is 1, and on the bottom it's 2. So in this case, we see that the degree of the numerator is less than the degree of the denominator. And more or less, that's part of what allows us to be able to do the method of partial fractions with that problem. So in this one, we don't have that, though. In this case, the degree of the numerator is actually larger than the degree of the denominator. Okay, which tells us that we have to take a different approach here. And our approach is going to relate to something that you may have thought that since we learned how to use calculators, that we no longer had to do ever again. And that thing that I'm going to talk about is long division. So a problem like, say, when we have 34 divided by 5, and we put it in this kind of form here. We're going to do a similar thing with the function that we have here. Again, because the degree of the numerator is larger than the degree of the denominator, we're going to set up a long division. The way that works is we take our numerator, in this case, so the thing on the top. So we're going to do that, 3r cubed, and we're going to divide that by the expression in the denominator, so the r squared plus 1. Okay, and even though we're working with coefficients and variables here, our process of doing this long division is going to be very similar to the way it works with the 34 divided by 5. So we know that when we're dividing these two, the first thing we do is determine how many times 5 can go into 34. The answer there is 6. So we know 6 times 5 is 30. We write that below and then we subtract. All right, so we do 34 minus 30 and we have 4 left over. So we're going to do a similar thing with the 3r cubed divided by r squared plus 1. Although we're just going to start by looking at how the leading term here, the r squared, how many times that goes into the thing that's being divided to 3r cubed. Or another way to ask that same question is, what do we have to multiply r squared by to give us 3r cubed? And the answer to that question is 3r. Because if we think about it, if we do 3r times r squared, we've got a 3 times, say, a 1 here, so it's a 3. And then r times r squared, we add the exponents, so it's the r squared is r to the first, so 1 plus 2. There gives us a 3, so we have 3r cubed. So I know that is correct. And just like we did with the 34 and the 6, we're going to go ahead and multiply the number, the thing that we put up here, by the expression down here. In order to do that, we need to multiply both terms by that. So we'll do our 3r times our r squared, which will give us 3r cubed, plus 1 times 3r is 3r. And then we'll go ahead and subtract. Okay. And when we do that, we note that the 3r cubed minus the 3r cubed, those two will cancel. And then there's nothing left here to subtract the 3r, but we still need to do that. So we have minus 3r left over. Okay. And then to kind of finish our division here, we do similar process to what we do in the long division to the left. So we look at, can 5 go into 4 any more times? It cannot. And so you may remember one way to think of this is this 4 is as the remainder. And we can put the remainder in a fraction in our answer as the remainder over what we divided by. So in this case, it'd be like 6 4/5. And so we'll do a similar thing on the right. So this negative 3r, that's going to be our remainder. And so we'll take that and put that over what we divided by, which was the r squared plus 1. So our expression up here would be 3r plus negative 3r over r squared plus 1, or I'm going to bring the negative sign down and make this minus 3r over r squared plus 1. Okay, and so that's what we get when we divide this function out. Now that's useful for us because we can go ahead and rewrite our integral now. So we can write this. Do it over here. So this integral of 3r cubed over r squared plus 1, we've just seen that this can be rewritten as the integral of what we got when we divided here. Okay, because remember, fraction is just the same as division. So what we did was just kind of write out the division here. So this would become 3r minus 3r over r squared plus 1 all dr. Now this thing here, this 3r minus 3r over r squared plus 1, I want to go ahead and integrate that. To integrate that, I'm going to break it into two pieces. So I'm going to have the integral of the first part, so integral of 3r dr minus the integral of the second part, 3r over r squared plus 1 dr. First part there, the 3r, we can use our power rule to integrate that. So we know it's like 3r to the first, can add 1 to that and get r to the second. So we know that the antiderivative here would be 3/2 r squared. Minus in the second integral, I'm going to go ahead and factor out the 3 here since it's a constant. This would be minus 3 times the integral of r over r squared plus 1 dr. And then we want to go after this integral here. And since we've been thinking about partial fractions in this section, we might think, how can we break that into a partial fraction? Notice, however, the denominator here does not factor. R squared plus 1 does not factor, so that won't work. But we may also notice that if we use a u substitution here, so I'm going to choose u equal to the denominator, the r squared plus 1, that gives us a du equal to 2r dr. We can divide by 2 on both sides there and make this 1/2 du equal to r dr. Now we can substitute back into our integral there. Looks like I ran out of some space. I'm going to have to go up here in the right-hand corner. All right, so now we're going to still have the 3/2 r squared minus 3 times the integral. Well, for r dr, we know we can substitute in our 1/2 du, and r squared plus 1 is equal to u, so we can substitute that in. So this would become 1/2 du over u. Factor out that constant of 1/2 there. So this would become 3/2 r squared minus another 3/2 times the integral of du over u. And we know that's like integrating 1 over u. So our antiderivative there would be 3/2 r squared minus 3/2 times ln absolute value of u. Substitute back in our value for u there. So the r squared plus 1 can go in for u. So I have 3/2 r squared minus 3/2 times ln absolute value r squared plus 1. And then we put in our plus c since this is an indefinite integral. All right. And that's what we get there. Now, one additional thing I'll say about this technique is we used it when the degree of the numerator was greater than the degree of the denominator, but we could also use it if the degree of the numerator was equal to the degree of the denominator. So as an example of that, if this integral had instead been integral of 3r squared over r squared plus 1 dr, we could have used a similar process here. All right, that's all I have for now. Thank you for watching.